हेलो। लास्ट वीडियो लेक्चर में हमने कुछ स्टैंडर्ड रिडक्शन फॉर्मूले किए थे। फॉर एग्जांपल फॉर इंटीग्रल 10 रेज टू पावर एन एक्स डी एक्स एंड फॉर इंटीग्रल सीकेंट रेज टू पावर एन एक्स डी एक्स। आज के इस वीडियो लेक्चर में हम रिडक्शन फॉर्मूले करेंगे फॉर इंटीग्रल साइन रेज टू पावर एन एक्स डी एक्स एंड कोस रेज टू पावर एन एक्स डी एक्स। सो लेट्स बिगिन with our first result. Yes, result is integral sine raised to power nx dx is equal to minus sine raised to power n minus 1 x into cos x divided by n plus n minus 1 divided by n integral sine raised to power n minus 2 x dx where n is not equal to 0. So let's see the proof. Consider the left hand side sine raised to power nx dx which is equal to sine raised to power n minus 1 x into sine of x dx. Now we solve this integral by integration by parts. So consider this as first function and this as second function. Now this is equal to first function as it is multiplied by integral of second minus cos x minus integral derivative of first n minus 1 sine raised to power n minus 2 x multiplied by cos x multiplied by minus cos x into में dx, which is further equal to minus sine raised to power n minus 1 x into cos x plus n minus 1 integral sine raised to power n minus 2 x multiplied by cos square x into dx. This is equal to minus sine raised to power n minus 1 x into cos x plus n minus 1 integral sine raised to power n minus 2 x, and we know that cos square x is equal to 1 minus sine square x. Now this is equal to minus sine raised to power n minus 1 x into cos x plus n minus 1 into integral sine raised to power n minus 2 x dx minus n minus 1 integral sine raised to power n x dx. Now taking this term to the left hand side, we have 1 plus n minus 1 multiplied by integral sine raised to power n x dx is equal to minus sine raised to power n minus 1 x into cos of x plus n minus 1 into integral sine raised to power n minus 2 x dx. Now this term 1 plus n minus 1 is n, so dividing both sides by n we get integral sine raised to power n x dx is equal to minus sine raised to power n minus 1 x into cos of x divided by n plus n minus 1 divided by n integral sine raised to power n minus 2 x dx. So this is our required reduction formula for integral sine raised to power nx dx. Similarly, we can prove the reduction formula for integral cos raised to power nx dx, and formula is cos raised to power nx dx is equal to cos raised to power n minus 1 x into sine of x divided by n plus n minus 1 by n integral cos raised to power n minus 2x dx. Now consider an exercise. Evaluate integral 0 to pi by 2 sine raised to power nx dx, where n is a natural number. So let's see the solution. Let this integral is in 0 to pi by 2 sine raised to power nx dx. So consider the first case. If n is equal to 1, in this case I1 is equal to 0 to pi by 2 sine x dx by putting n is equal to 1, and we know that integral of sine x is minus cos x, and limit goes from 0 to pi by 2. By putting upper limit and lower limit, we have minus cos pi by 2 plus cos 0, and we know that cos pi by 2 is 0 and cos 0 is 1, so answer is 1. For the case n equal to 1, we have integral I1 is equal to 1. Now consider the next case. If n is greater than or equal to 2, then we know that integral sine raised to power nx dx is equal to minus sine raised to power n minus 1 x multiplied by cos of x divided by n plus n minus 1 by n into integral sine raised to power n minus 2 x dx. Now taking limit from 0 to pi by 2 on both sides, we get integral 0 to pi by 2 sine raised to power nx dx is equal to minus sine raised to power n minus 1 x into cos x divided by n, and limit goes from 0 to pi by 2 plus n minus 1 divided by n integral 0 to pi by 2 sine raised to power n minus 2 x dx. Now on the right hand side, in the first term, if we put x is equal to upper limit, which is pi by 2, then we know that cos pi by 2 is 0 and sin pi by 2 is 1, so 0 multiplied by 1 is 0. And if we put the lower limit 0, then sine 0 is 0 and cos 0 is 1. So our value is again 0. So first term is 0 minus 0 means 0, plus second term is n minus 1 divided by n multiplied by 0 integral 0 to pi by 2 sine raised to power n minus 2 x dx. So our left hand side is in, which is equal to right hand side n minus 1 by n, and the integral on right hand side, if we see, in is equal to 0 to pi by 2 sine raised to power nx dx. If we replace n by n minus 2, then this integral is in minus 2. Let's say this is equation 1. Now replacing n by n minus 2 in first, we have in minus 2 is equal to n minus 2 minus 1 divided by n minus 2 into in minus 4, which is equal to n minus 3 divided by n minus 2 in minus 4. So putting this value of in minus 2 in first, we have in is equal to n minus 1 divided by n multiplied by n minus 3 divided by n minus 2 into in minus 4. Similarly, by replacing n by n minus 4 in first, we get the value of in minus 4 in term of in minus 6 and so on. Now further consider the case if n is an even positive integer, then in will be n minus 1 by n multiplied by n minus 3 divided by n minus 2 multiplied by n minus 5 divided by n minus 4 and so on. At the end, 1 by 2 I naught, where I naught is equal to integral 0 to pi by 2 sine raised to power 0 x dx. And we know that sine raised to power 0x is 1. So 0 to pi by 2 1 dx, which is equal to x limit goes from 0 to pi by 2. Now by putting upper limit minus lower limit, we get pi by 2 minus 0 means pi by 2. So in this case, in is n minus 1 multiplied by n minus 3 multiplied by n minus 5 and so on, 1 divided by n multiplied by n minus 2 multiplied by n minus 4 and so on, 2, and multiplied by I naught, which is pi by 2. Now consider the remaining case, case 2. If n is an odd positive integer, in this case In is n minus 1 by n into n minus 3 by n minus 2 into n minus 5 by n minus 4 multiplied by, and so on, at the end multiplied by 2 by 3 and multiplied by I1, and we know that I1 is, which is calculated already, I1 is 1. So putting this value of I1 in this, we get In is equal to n minus 1 multiplied by n minus 3 multiplied by n minus 5 and so on, 2 divided by n into n minus 2, n minus 4 and so on, 3, and multiplied by 1. So finally we have integral 0 to pi by 2 sine raised to power nx dx is equal to, yes, in both the cases, if we see the pattern of this term, we can see that numerator part n minus 1 multiplied by, go on decreasing by 2, and divided by numerator part n multiplied by, go on decreasing by 2, and this whole term is multiplied by, case wise, multiplied by this term is pi by 2 if n is even, and multiplied this term by 1 if n is odd. So this is our final result for the integral 0 to pi by 2 sine raised to power nx dx, and this formula is known as, this formula is called Wallis formula. Now in this similar way, we can prove integral 0 to pi by 2 cos raised to power nx dx is equal to n minus 1 multiplied by, go on decreasing by 2, divided by n multiplied by, go on decreasing by 2, and this whole term is multiplied by pi by 2 if n is even, and multiplied by 1 if n is equal to a odd positive number, and this is also known as Wallis formula, and both formula are same. Now consider some exercises. First one is evaluate the integral 0 to a x raised to power 4 divided by square root a square minus x square dx. So let's see the solution. Let this integral is I 0 to a x raised to power 4 divided by square root a square minus x square dx. Now put x is equal to a sine theta, then we know that dx is equal to a cos theta d theta, and when x is equal to 0, theta is 0 and x is equal to a sin theta is equal to a means sin theta is equal to 1 means theta is equal to pi by 2. So integral I becomes 0 to pi by 2 sin raised to power 4 theta divided by square root a square minus a square sin square theta multiplied by dx, which is a cos theta d theta. Here sin raised to power 4 theta should be a raised to power 4 sin raised to power 4 theta. Now simplifying this term, integral 0 to pi by 2 a raised to power 4 sin raised to power 4 theta into a cos theta divided by, now taking a square outside this square root, we get a into square root 1 minus sin square theta into d theta. Now cancelling a to a, 0 to pi by 2 a raised to power 4 sin raised to power 4 theta divided by, we know that 1 minus sin square theta is cos square theta, so our denominator is cos theta and this term is multiplied by cos theta d theta. Now cancelling cos theta and cos theta, we get a raised to power 4 multiplied by integral 0 to pi by 2 sin raised to power 4 theta into d theta. Now integral 0 to pi by 2 sin raised to power 4 theta d theta can be written by Wallis formula, denominator 4 into 2 and numerator part 3 into 1, and because 4 is an even number, so this whole term is multiplied by pi by 2. So answer is a raised to power 4 multiplied by 3 pi divided by 16. So this is the answer. Consider another exercise. Evaluate the integral 0 to 3 pi by 2 cos raised to power 5 theta by 3 d theta. Let say this integral is I, 0 to 3 pi by 2 cos raised to power 5 theta by 3 d theta. Now put theta by 3 is equal to x. So d theta is equal to 3 dx, and when theta is 0, x is 0 and theta is equal to 3 pi by 2, x is pi by 2. So integral is 0 to pi by 2 cos raised to power 5 x multiplied by 3 dx, which is equal to 3 times integral 0 to pi by 2 cos raised to power 5x dx. Now for this integral, again using Wallis formula, for integral 0 to pi by 2 cos raised to power nx dx, and formula is 3 multiplied by, in the denominator part 5 go on decreasing by 2, 5 into 3 into 1, and numerator part 4 into go on decreasing by 2, 4 into 2, and for the odd integer which is here 5, we have multiplied factor is 1. So answer is, cancelling 3 to 3, answer is 8 by